Hello, my name is Matthew Keene. I am in Professor Curtis's section, which is section B, and this is my lab report on Lab 3, Black Hole and Orbits. So the purpose of this experiment was to analyze how differing masses and forces affect orbits of objects and gravitational motion. So right here I have the formula for the perpendicular force of an object in circular motion, the perpendicular component, and I also have the net force, Newton's second law, in relation to momentum, which is important because the parallel component of an object moving in a circle or an ellipse, its parallel component is equal to this. So the results of this experiment were that objects traveling in an elliptical orbit will experience different parallel and perpendicular forces based on their location and have larger or smaller velocities as they travel. So as this object gets closer to the black hole, it speeds up, and as it gets further away, it slows down because its potential energy is increasing, so its kinetic energy therefore decreases. So the setup for this, our system was the star and the black hole. I have my code here. Some of it got a little bit cut off, but these are the initial conditions I have. So I have the star's mass, I have my delta t, I have my initial time, which is t equals 0, and my gravitational constant. I also have the calculations for Newton's second law to calculate F net parallel and F net perpendicular. So these are the formulas for that. And then I also have the lines of code that calculate the mass of the black hole. So here you can see I'm multiplying the magnitude of F net by the radius squared, which is the distance between the sun, or sorry, not the sun, the star and the black hole, and then dividing that by the gravitational constant and the star's mass. And then, yeah. So what does this mean? Based on the results, you can see that the parallel and perpendicular components of the force affect the parallel and perpendicular components of momentum, since force comprises of the derivative of momentum over time with respect to time, and the momentum of the star changes in magnitude and direction when it's acted upon by the mass and then therefore the gravitational force of the black hole. And since the momentum is conserved, we can calculate the mass of the black hole using the conservation of momentum and the conservation of energy principles, and no energy is dissipated into the surroundings since it's isolated. And here we have the orbit of the spaceship, which is part 2 of the lab. And so because we're given the initial speed of the moon and also the spaceship, we can calculate the vector components that the moon and the planet and the spaceship all have on each other using Newton's law of gravitation. So over here you can see I have all of my initial values, and I also have the speed of my moon, and I found this using the position vector, and then also the velocity, which is just the vector of the moon's speed because it has direction. And then over here I have my ship's initial velocity and position, or sorry, not initial position, initial speed, and then I calculated the vector component of that, which is the velocity. And here is the vector calculations for each one. So this is the net force on the spaceship, and this is the net force on the moon. And you can see that I have my r hats and my forces, as well as over here. It's kind of a lot. I'm not going to read all of it off. And here's where I calculated the actual force and updated the velocity and position based on the force that I calculated using the vectors on the previous slide. And here was my result, and that's with the correct velocity, the spaceship is able to orbit the planet and the moon without crashing. So you can see a little animation here. Kind of cool, kind of awesome. And it has the orbital speed as well as the period. So what if the system included more than just the star and the moon and the spaceship? We'd have to calculate the motion using the mass and gravitational force exerted by the black hole, and it would affect the path of all of the objects within the system. And that's it. Thank you.